Imagine a massive array of servers running the next great artificial intelligence training model.
Right, something with trillions of parameters.
Exactly. Trillions of parameters, just crunching petabytes of data, searching for like a breakthrough in protein folding or maybe material science.
And the thing is, that physical machine, it really doesn't care where it is.
No, it doesn't. It doesn't care if it's cooled by the freezing ambient air of the Arctic Circle or, if it's drawing current from some vast solar farm just baking in the Arabian desert.
Yeah, it only demands one thing, and that is constant, unrelenting, just massive amounts of electricity.
Which brings us to the core of what we're talking about today, because if you, listening to this right now, were to map out the global power dynamics of the 21st century, you wouldn't be charting gold deposits or oil fields anymore.
No, the map has completely changed.
It has. You'd actually draw a map of where the absolute cheapest electrons on Earth are generated. Because that hidden geography, that's the literal blueprint for the future of human intelligence.
We are, without a doubt, witnessing a fundamental rewriting of spatial economics. I mean, for the last century, industrial centers had to be located near raw materials, right?
Right, or major shipping lanes.
Exactly. But the calculus has entirely shifted now. The new economic epicenter is really defined by the physical locations where sunlight, wind, and gravity-fed water converge.
And converge with the highest efficiency and the lowest cost.
Yes, because the commodity being transported today isn't physical goods in shipping containers, it's raw computational power.
Which just gets transmitted via fiber optics.
Precisely.
And that structural shift, that's the entire focus of our deep dive today. We've got this fascinating stack of analytical writings from the Netizen blog to unpack for you.
Like a really comprehensive set of sources.
It really is. It presents this rigorous economic breakdown of global electricity generation. And then it contrasts that with the just staggering, almost incomprehensible energy appetite of the exploding AI sector.
And it all culminates in a highly specific real-world case study.
Right. They argue that remote regions, specifically the high-altitude river systems of Nepal, actually are uniquely positioned to become the engine rooms of this new digital economy.
Which is a massive claim.
A huge claim. So our mission today is to test that thesis. We're going to figure out where the cheapest electricity on Earth actually comes from, why the AI industry is desperately hunting for it, and how we might bridge that gap.
And we'll look at whether a 50-gigawatt bet in the Himalayas is actually a visionary strategy or just an engineering impossibility.
So to understand the viability of that Himalayan strategy, or honestly any energy strategy moving forward, we kind of have to start with the foundational metric that the sources use throughout.
Yeah, we have to talk about LCOE.
Right, levelized cost of electricity, which is basically the master key for comparing completely radically different energy sources.
It's essential, because otherwise you're comparing apples and oranges.
So let's ground LCOE before we get into the global data, because I want to make sure I'm wrapping my head around this correctly.
Sir, go for it.
My read on this metric is that it functions basically like calculating the lifetime miles per gallon for a power plant, but, translated into dollars.
That's actually a really great way to put it.
Because it's not enough to look at a solar panel and just say, well, the sunlight is free, so the energy must be free.
Right, because the hardware certainly isn't free.
Exactly. You have to calculate the cost of the raw silicon, the manufacturing, the shipping, the labor, to physically bolt it to the ground in the desert.
And don't forget the financing. The interest rate on the loan you took to build the farm.
Yes, the interest rate and the maintenance over, say, 25 years. You take every single dollar spent from the day you dream up the project to the day you decommission it, and you divide it by every single megawatt hour of electricity that panel will realistically produce over its entire lifespan.
That is the precise mechanism, yes.
Huh.
LCOE amortizes the capital expenditure, the operational expenditure, and the cost of capital against the total lifetime output.
And you mentioned the cost of capital. The text seems to really emphasize that.
Oh, it's critical. A 2% interest rate versus an 8% interest rate. I mean, that fundamentally alters the LCOE of a capital-intensive project like a hydro dam.
Because you're borrowing billions up front.
Exactly. So by standardizing all these variables, LCOE kind of strips away the noise. It lets us look at a nuclear reactor in France, a geothermal well in Iceland, and a solar farm in Oman, and determine exactly what one unit of energy costs to produce in a free market.
Okay, that makes perfect sense. So Let's unpack this. When we apply that metric globally, the geography of cheap electrons becomes incredibly distinct.
It really does. The data points from the sources indicate that geography dictates over 50% of the economics of power.
Over 50%, just based on where you put it.
Exactly. Location is everything.
So let's look at the deserts first. The Middle East, so Saudi Arabia, the UAE, Oman, and North Africa. The sources note that we are seeing solar PV costs that have just plummeted 90% since 2010.
It's an unprecedented deflationary curve.
It's wild. The text points to recent record auctions hitting between $10 and $20 per megawatt hour.
Which is essentially practically free in historical terms.
Right, but on a physical engineering level, achieving a $10 megawatt hour requires maximizing multiple variables simultaneously, right?
It does. It requires a perfect optimization of irradiance, land cost, and supply chain scale.
So break that down for us. What's happening in these Sunbelt regions?
Well, first you are dealing with exceptional solar irradiance. The sun is just incredibly intense and consistent, which yield capacity factors well over 25 to 30%.
Wait, capacity factor? It means the panels are producing at their absolute maximum rated capacity for roughly a third of the year?
Yes, compared to an installation in, say, Germany or the UK, where it might be much lower, simply because the sun is more intense near the equator and cloud cover is practically non-existent.
Okay, so the fuel, the sunlight is maxed out. What else?
Furthermore, these regions offer vast expanses of low-cost, non-arable land. You aren't competing with agriculture or urban development for real estate.
Oh, right. A farmer isn't trying to outbid you for desert sand.
Exactly. So when you combine those high capacity factors, near zero land acquisition costs, and then you add in the massive deflationary curve of Chinese solar hardware manufacturing.
Because the panels themselves are getting so incredibly cheap to make.
Right. You compress the LCOE to that $10 floor.
But let me push back here, or at least introduce the physical constraint the text mentions. Because if solar is sitting at $10 to $20 a megawatt hour in the Arabian desert, the obvious question you or I would ask is, why hasn't the global energy market completely reoriented around the Sahara?
Ah, yes. The friction point.
Right, and the friction point is transmission. You can generate the absolute cheapest electron in human history in the middle of a desert. But if you don't have a multi-billion-dollar high-voltage direct current line to carry it to a major metropolis...
Or grid-scale batteries to hold it until nightfall.
Exactly. If you don't have those, the economic value of that electron effectively drops to zero. It just becomes stranded power.
And the problem of stranded power is the central bottleneck that sources identify. Generation is really only the first half of the physics equation.
Delivery is the second half.
Exactly.
Yeah.
And that constraint isn't just limited to solar in the deserts. We actually see the exact same dynamic when we move to the next geographic hotspot in the analysis.
Which is onshore wind, right?
The text highlights the high plains and steppes. So we're looking at China's northern regions, the U.S. Great Plains, and the vast windswept expanses of Patagonia.
You know, the mechanics of wind power generation are fascinatingly different from solar. I was geeking out over the physics of this while reading the source material.
Yeah. What stood out to you?
Well, it apparently all comes down to the cube of the wind speed. The kinetic energy available to a wind turbine isn't linear at all. If the wind speed doubles, the power available doesn't just double.
Right. It increases by a factor of 8.
A factor of 8. That's insane.
Which is exactly why geography is so incredibly deterministic for wind LCOE. In places like Patagonia or the U.S. Great Plains, the wind resource isn't just strong.
It's consistent, right?
Yes, it possesses high laminar flow, which is an engineering term, meaning it is incredibly consistent with very minimal turbulence.
So the turbines aren't getting battered around randomly.
Exactly. And when you place modern turbines into those highly consistent corridors, and keep in mind, these new turbines feature massive swept areas with blades exceeding 100 meters in length.
They're absolute monoliths.
They are. When you put them there, you achieve capacity factors that can actually rival or even outcompete solar in prime spots.
The text mentions China has aggressively exploited this in their northern provinces, driving their onshore wind LCOE down to parity with their solar installations.
They have. It's a massive localized advantage.
So solar and wind are these huge disruptors, basically driving the marginal cost of energy towards zero when the weather cooperates. But the sources also focus really heavily on the structural heavyweights of the grid, which are geothermal and existing hydropower.
Right, the traditional giants.
We're looking at geothermal in the East African Rift through Kenya, the volcanic geology of Iceland, and places like Indonesia. And then we have massive legacy hydropower in Canada, Norway, Brazil, and China.
And the mechanical differences here are crucial to understand.
Definitely. I was thinking about it like this. Solar and wind are like a microwave.
A microwave. Okay, I'm intrigued.
Yeah, they're incredibly fast, they're super cheap to operate, but they only heat up your food or generate power when you're actively pushing the button, when the sun is actively shining or the wind is blowing.
Okay, I see where you're going with it.
But hydropower and geothermal, they're like a slow cooker. You
Yeah.
plug it in and it's just always on. It provides this incredibly reliable constant heat, or in this case, base load power.
I actually love that analogy because the concept of physical inertia is key to understanding the value of hydro and geothermal.
Expand on that. What do you mean by physical inertia?
Well, these sources provide baseload, dispatchable power, meaning you can turn it on demand. Geothermal taps into the thermal inertia of the Earth's crust, yielding capacity factors that frequently exceed 90%.
90%, that's almost always on.
Exactly. You're getting essentially free heat from the Earth. And with hydropower, the mechanism relies on head.
Head, like water head.
Right, the vertical drop of gravity pulling water down through a penstock.
Yeah.
You spin up a multi-ton steel turbine, and its sheer mechanical momentum provides immense frequency stability to the electrical grid.
It acts like a massive mechanical flywheel.
Yes. And once the staggering initial capital cost is paid off, the cost of pouring literally millions of tons of concrete to build the dam.
Right. Once that's amortized, the operational cost is effectively zero. You are just managing the hydrology of rain and snowmelt.
This is the exact economic reality for regions like Quebec or Norway today. They benefit immensely from legacy infrastructure built decades ago.
Their current LCOE is practically unmatched because the capital costs have just vanished from the ledger. It's fully paid off.
Exactly, allowing them to offer these rock-bottom industrial power rates today.
Which brings us to a really critical distinction the source material makes, and this is important. We have to separate structural cheapness from artificial cheapness.
Yes, the text explicitly examines fossil fuel generation in heavily subsidized environments.
Right, specifically natural gas and coal in places like Iran, Russia, and certain Gulf states. The data points out that residential electricity in Iran sits around 0.3 of a U.S. cent per kilowatt hour.
0.3 of a cent. It's almost free.
Wait, really? How is that even possible from an LCOE perspective?
Well, it's not. We have to carefully distinguish between actual market production costs and state-engineered consumer prices. An LCOE analysis measures the raw cost of extracting, refining, and burning that natural gas.
The actual physical and labor costs.
Exactly. When a consumer in Iran pays fractions of a cent, that price does not reflect the LCOE. It reflects a government policy that intentionally forgoes the opportunity to sell that gas on the open global market at a massive premium.
They absorb the cost to provide subsidized power domestically. And to be completely clear for everyone listening, we are analyzing this strictly through the lens of market economics today, exactly as the source material does.
Right. We're just reporting the economic analysis.
Yeah.
We aren't taking any stance on the political or ethical dimensions of domestic subsidy policies.
Exactly. But the purely economic consequence that the text points out is that heavy energy-intensive industries will often relocate to these subsidized environments just to capitalize on the artificially depressed rates.
Naturally, capital seeks the lowest cost.
But the text also argues this model is inherently volatile long-term. Subsidies are subject to macroeconomic shocks, and the long-term viability is threatened by the global pricing of carbon emissions.
Right. The author makes a strong case that it's a localized economic distortion. It's not a scalable structural decline in energy costs like we see with next-generation renewables.
And that distinction between a temporary price distortion and a permanent technological deflation is so vital for the next part of our discussion.
Because the entity currently searching the globe for cheap power doesn't just need a few megawatts for an aluminum smelter.
Here's where it gets really interesting. We've mapped out these geographically locked pockets of ultra-cheap power globally. Who is the new desperate buyer?
Artificial intelligence.
Yes. The sheer scale of the energy required for AI compute is staggering. According to the text, global AI data centers consumed roughly 415 terawatt hours of electricity in 2024.
To contextualize a terawatt hour, we're talking about energy consumption that rivals the entirety of industrialized mid-sized nations.
Yeah, that's like a whole country's worth of power. The sources say that 415 terawatt hours represents about 1.5% of the entire world's electricity use.
And we have to emphasize that 415 terawatt hours is merely the baseline of the adoption curve.
It's just the beginning.
The projections cited in the source material model, this demand more than doubling to 945 terawatt hours by 2030. AI server deployments are expanding at a 30% compound annual growth rate.
30% year over year. That's massive.
The analysis even estimates that data centers in the United States could scale from demanding 4% of the national grid today to anywhere between 7 and 12% within the next decade.
But wait, how do we know this isn't just a bubble? We have to distinguish this from previous tech-driven power surges, right? Like cryptocurrency mining.
Ah, that's a crucial difference the expert analysis in the text makes. Crypto demand was highly elastic.
Right, it spiked when token prices were high and completely collapsed during bear markets. Miners would literally just unplug their rigs.
Exactly. But the source material argues that AI demand is fundamentally structural. It's bottomless.
Because it encompasses so many different layers of computing. It's the massive, months-long asynchronous training runs for large language models, plus the real-time inference load every single time an end user queries an AI.
Plus the back-end integration of machine learning into almost all enterprise software moving forward. The demand curve is practically infinite because intelligence itself is a universally applicable input.
But accommodating that demand introduces severe physical friction. I mean, the infrastructure requirements for a modern AI data center, specifically the thermal management of these high-density GPU clusters, are incredibly complex.
I run it incredibly hot.
So let me channel a common concern here, because I think a lot of listeners will be wondering this. When people hear those massive numbers going up to 945 terawatt hours, their first instinct is usually panic.
Sure, they worry about grid strain, water use, emissions.
Yeah. Right. We are seeing real-world examples right now where grid infrastructure is simply maxed out. Neighborhoods are facing potential brownouts, and the millions of gallons of water required for cooling these server farms are draining local aquifers. So, shouldn't we be hitting the brakes? Is rationing the logical response?
That is definitely the prevailing sentiment in many regulatory circles right now. But the Netizen blog aggressively counters that logic.
Oh, really? How so?
Drawing directly from the text, they introduce this concept of the age of abundance. The core economic thesis here is that AI compute is not a zero-sum subtraction from the broader economy.
Okay, so it's not like AI is just stealing power from hospitals and homes.
Exactly. It is a compounding multiplier. The logical response isn't rationing, because every marginal kilowatt hour applied to AI yields outsized economic returns.
So the argument is that you don't starve the engine that's designed to solve the very constraints you're worried about.
Precisely. The computational power we are debating rationing is currently being utilized to accelerate drug development, to discover novel battery chemistries, and to optimize the routing algorithms of our existing power grids to reduce transmission loss.
So the thesis is that using AI to, say, design a more aerodynamically efficient wind turbine blade ultimately generates far more power than the AI consumed to run the simulation in the first place.
Exactly. The sources argue for solving these grid challenges through innovation rather than constraining supply.
Like advanced liquid cooling or closed-loop water recycling.
Right, or even AI optimizing its own next-generation silicon to offer higher floating point operations per watt. The author's underlying warning is pretty stark. If a region chooses to artificially constrain power supply to AI out of caution, they are actively ceding technological leadership.
They lose the race to jurisdictions that just embrace energy abundance.
It's an infrastructure arms race. Historically, massive expansions in available energy, like the electrification of factories or the widespread adoption of the internal combustion engine, those have always triggered unprecedented economic output.
So the text is basically positing that computational power is the new oil, and restricting its flow is economic self-sabotage.
That's the argument, yes.
But accepting the necessity of energy abundance brings us right back to our original physics problem. We know the AI needs limitless power, and we know the cheapest power is locked in places like the Arabian Desert or the Patagonian steppes.
Right.
And as we established earlier, you can't just run a high-voltage extension cord across the Atlantic Ocean. So how do the tech hyperscalers bridge the gap between their massive demand in Silicon Valley and the cheap supply in the Sahara?
Well, if we connect this to the bigger picture, the solution lies in realizing that the demand for AI compute, particularly the training phase, is inherently borderless.
Borderless, meaning they don't have to build data centers in crowded, expensive cities anymore.
Exactly. The source material highlights a massive strategic pivot. Hyperscalers are relocating the compute directly to the generation's source.
The phrase the text uses, and I love this, is exporting intelligence, importing electrons indirectly.
It's a radical shift in logistics.
It really is. Because latency requirements usually dictate this stuff, right? Like, you can't put a high-frequency trading server in Kathmandu and expect to beat the stock market in New York. The speed of light through fiber optics just creates too much lag.
But an AI model training run is asynchronous. It takes months.
Right. So it literally doesn't matter if that server rack is sitting next to a hydro dam in a remote mountain valley. You feed it the localized, ultra-cheap power, and you just transmit the final processed algorithmic model intelligence back to the global market.
You are bypassing the physical limitations of the electrical grid by utilizing the global telecommunications network. You transmit the answers, the data, not the raw power.
And to fund this, tech companies are utilizing these massive power purchase agreements, or PPAs, right?
Yes, they use PPAs to directly underwrite the capital costs to construct new renewable generation precisely where they want to locate their data centers.
Which leads to a really counterintuitive strategy outlined in the sources regarding these new builds, the concept of overbuilding renewables.
This is a fascinating part of the text.
Because if a hyperscaler needs, say, a firm 100 megawatts to run a facility, the text actually advocates funding 150 megawatts of solar or wind capacity.
Which, on a traditional grid, creates a massive headache called curtailment.
Right, because you literally have to shut the turbines down when the wind blows too hard because there is nowhere for the surplus electricity to go, and it destabilizes the grid frequency.
Curtailment is a massive economic inefficiency. However, an AI data center operates as the ultimate flexible load. It acts as an economic sink for that overbuilt capacity.
Because the computing workload can be dynamically scaled up and down.
Yes. Through demand response software, the facility can ramp up its non-time sensitive workloads like ingesting massive new datasets or running complex simulations during periods of peak solar irradiance or high wind speeds when the power is effectively free.
And then when the generation drops, say the wind dies down, the data center throttles down the asynchronous compute, maintaining only critical inference operations. That's incredible. It smooths out the intermittency of the renewables entirely.
It does.
Yeah.
And this dynamic load matching creates a really powerful virtuous cycle identified in the text.
Right, the cycle where the localized cheap power attracts massive capital investment for the AI data center. That capital underwrites the overbuilding of generation, and the resulting energy surplus acts as a magnet for even further industrial development in the region.
It's a self-sustaining loop of infrastructure growth.
So what does this all mean in the real world? Because the abstract theories of borderless demand and dynamic load matching are intellectually compelling, but the Netison sources force us to ground this in reality through a highly detailed case study.
Yes, they apply this entire macroeconomic framework to a very specific, incredibly challenging geography. Nepal.
Which serves as kind of the ultimate stress test for this whole age of abundance thesis.
We're looking at a nation situated entirely within the highest mountain range on Earth, possessing one of the most formidable untapped energy profiles globally.
The raw hydrology detailed in the text is just staggering. The rivers cascading down the Himalayas give Nepal a theoretical hydropower potential of roughly 83,000 megawatts, or 83 gigawatts.
Now, the sources clarify that when you filter that theoretical number through topographical and geological constraints, about 42,000 to 43,000 megawatts are considered economically viable for development.
Still a massive number, but as of mid-2025, their total installed capacity is only hovering between 3,400 and 4,000 megawatts. They have harnessed less than 10% of their viable resource.
The disparity between potential energy and realized infrastructure is vast, but the economic incentive to close that gap is clearly outlined in the LCOE projections for well-sited hydro projects in Nepal.
What are the numbers looking like?
They sit between 2 and 10 cents per kilowatt hour.
Wow, 2 to 10 cents.
And crucially, as we established earlier with our mechanical flywheel concept, this is dispatchable, baseload-like power. It perfectly complements intermittent solar and wind.
It offers the exact frequency stability that hyperscale data centers require to run 247 without relying solely on massive, expensive battery banks.
Which is why the source material argues that executing a 50-gigawatt build-out in Nepal isn't just a domestic infrastructure project.
No, it's a strategic maneuver to capture a huge slice of the global AI compute market. It's a 50,000 megawatt bet.
Exactly. But to understand the viability of that bet, we really have to examine the engineering mechanics.
Hmm.
Nepal's hydrology is entirely dictated by the South Asian monsoon.
Right, you have these extreme weather patterns.
The river systems experience massive violent flows during the summer and then recede significantly during the winter dry season.
Which means you cannot rely solely on run-of-river hydro projects. While they are faster to construct and require less capital, their power output just plummets precisely when you need firm, year-round baseload for a data center.
The source is explicit that a successful strategy requires a hybrid approach. You must blend the cheaper run-of-river installations with massive storage hydro projects.
Storage dams. These create deep reservoirs that function as immense gravitational batteries, right?
Yes, they capture the excess kinetic energy of the monsoon floods, hold it in reserve, and release the water through the penstocks during the dry months.
Ensuring a completely flat, unwavering power output curve throughout the year. But the scale of the mega projects mentioned in the text to achieve this is just difficult to conceptualize.
They cite the Karnali Chisapani project, for instance.
Yeah, that one has a potential of 10,800 megawatts, a single installation that would more than double the entire current capacity of their national grid.
And they also point to the Pancheshwar multi-purpose project, projected at around 5 gigawatts.
These are engineering feats on par with the largest infrastructure projects in modern history.
They are. But introducing projects of this scale inevitably brings us to the most critical friction point in the entire thesis.
The timeline of capital deployment. Because traditional hydropower construction takes forever, right?
It is glacially slow. It requires years of complex geological surveying, environmental impact studies, and traditional drill and blast excavation.
And if the AI compute demand is currently skyrocketing toward 945 terawatt hours by 2030, a dam that takes 15 years to build just misses the wave entirely. The compute will simply locate somewhere else.
Exactly.
So how does Nepal get to 50 gigawatts fast enough to catch this AI wave? How do they overcome that temporal hurdle?
The roadmap provided by the source relies on aggressive, highly capital-intensive execution strategies designed specifically to compress the timeline. And the most significant technological shift they point to is the deployment of tunnel boring machines, or TBMs.
Oh, man. For those listening who aren't familiar with civil engineering at this scale, a TBM is not a simple drill. It is literally an underground mechanized factory.
It's an incredible piece of machinery.
Instead of the traditional method of, drilling holes, setting explosives, blasting the rock, clearing the debris, and then reinforcing the tunnel wall, which is incredibly slow and dangerous, a TBM uses a massive rotating cutter head to just grind through the solid geology.
And crucially, as it moves forward, it simultaneously installs precast concrete segments to line the tunnel behind it.
It builds the tunnel while it digs. The utilization of TBMs exponentially accelerates the excavation of the headrace tunnels that funnel the water to the subterranean powerhouses.
Furthermore, the text emphasizes modular construction techniques.
Where massive electromechanical components are prefabricated off-site and integrated rapidly.
Yes, but accelerating the timeline with TBMs and modular construction requires massive upfront capital.
A single TBM costs tens of millions of dollars before it ever touches a single rock. And the financial risk premium on these projects is enormous because the interest on the debt accumulates for years before the first electron is even sold. Nepal simply cannot unilaterally finance a 50-gigawatt expansion.
Which is why the source material heavily emphasizes international syndication.
They need global partners.
Exactly.
Yeah.
The execution of these mega projects requires intricate engineering, procurement, and construction contracts, EPCs, that distribute the financial and technical risk across global stakeholders.
And the text provides concrete examples showing this framework is already functional, right? They reference the Upper Tamakoshi project at 456 megawatts.
Which served as a massive capacity-building exercise for domestic engineering.
But then they quickly scale up to international collaboration, pointing to the Upper Trishuli 1 project at 216 megawatts. That one brought in Korean developers and financing from the International Finance Corporation.
Furthermore, major Indian developers like SJVN are currently executing the massive Aran 3 and Lower Aran projects.
This demonstrates a proven template for public-private partnerships. It facilitates critical technology transfer from Chinese, Indian, Korean, European, and North American firms who possess the specialized manufacturing capabilities for large-scale hydro turbines and digital control systems.
It requires a truly global effort.
Yeah.
But even with international financing and advanced TBMs, we have to address the physical realities of the Himalayas.
Yeah, the geological and environmental hurdles the sources raise are intense. The Himalayas are the youngest, most tectonically active mountain range on the planet. The seismic risk is profound,
It is. Earthquake engineering for massive concrete arch dams or earth-fill storage dams requires immense structural redundancies.
which inherently drives up the capital cost.
And additionally, the young geology means the mountains are constantly eroding. This leads to extreme sedimentation rates in the river systems.
And sedimentation is lethal to hydropower. The text describes it like liquid sandpaper.
That's exactly what it acts like.
High-velocity silt just causes rack decavitation and abrasion, literally destroying the steel blades of the turbines. And if a reservoir fills with silt, the water battery loses its entire storage capacity.
So the engineering solutions presented in the text to combat this are fascinating. They include specialized sediment flushing gates built right into the base of the dams.
How do those work?
Well, these systems rely on complex fluid dynamics to induce what are called turbidity currents. Essentially, they utilize the river's own flow to scour the silt from the reservoir floor and flush it through the system during high-flow events.
So the river cleans the dam itself.
Exactly, preserving the longevity of the infrastructure.
But the engineering challenges are really only half the equation here. The text rightfully dedicates significant focus to the socioeconomic impacts, because you cannot flood entire valleys and alter river ecosystems without profound consequences for the local communities.
Absolutely not. If a mega project is viewed purely as an extractive enterprise by foreign capital, it will face intense project-killing local resistance.
So what are the solutions the source advocates for?
The policy mechanisms are centered on mandated benefit sharing. This requires integrating the local communities directly into the economic upside of the project.
We're talking about equity shares for the local population, giving them real ownership.
Right, and guaranteeing comprehensive rural electrification alongside the high-voltage transmission lines.
And designing the storage dams with multi-purpose synergies too, right? Like providing regulated irrigation flows for downstream agriculture during the dry season.
Exactly. The framework suggests that if the socio-economic alignment is handled correctly, the result is an enduring economic engine for the whole region. Because even if Nepal successfully lures massive AI data center clusters to utilize a portion of that 50 gigawatts, they will still possess a massive energy surplus.
And that surplus creates immediate, bankable foreign exchange revenue. The text highlights existing cross-border power purchase agreements with India, who has an insatiable demand for clean baseload to power their own industrial growth.
And there's also the potential for dedicated transmission corridors through India to supply Bangladesh.
So ultimately, the source material's deep dive into Nepal is kind of a microcosm of the entire global energy transition.
It really illustrates the sheer magnitude of capital, engineering ingenuity, and complex international diplomacy required to bridge the gap between geographical potential and digital necessity.
It's an incredible synthesis of the massive forces shaping our future. I mean, we started this journey by breaking down the levelized cost of electricity to understand why a $10 electron in the Arabian desert fundamentally alters the global market.
We mapped the immense kinetic potential of wind corridors in Patagonia and the relentless thermal baseload of Iceland.
We confronted the chilling reality of the AI industry's trajectory toward consuming 945 terawatt hours, and we examined how tech hyperscalers are literally rewriting the rules of logistics by exporting intelligence and importing electrons.
And finally, we analyzed the incredibly complex 50-gigawatt blueprint required to turn the cascading rivers of the Himalayas into a primary engine for human computation.
The overarching thesis of the Netizen blog proves incredibly robust under scrutiny. We are moving decisively into an era where the constraints on human advancement are no longer theoretical or algorithmic.
No, they are strictly physical. The code has already been written. The limiting factor is now the availability of concrete, copper wire, and raw thermodynamic energy.
The expert analysis in the text leaves us with a profound realization. Abundant, low-cost electricity has unambiguously replaced petroleum as the foundational commodity of the modern economy. In the AI age, cheap electricity is the new oil.
It completely reframes the entire concept of a superpower. The ultimate geopolitical moat is no longer just a deep-water port or a vast oil reserve.
It is the capacity to generate clean, unrationed power at scale. The ultimate enabler of human progress is no longer just lines of code. It is the physical electrons flowing through copper.
It really makes you look at the world differently.
It does. So, as we wrap up this deep dive, I want to leave you, the listener, with a final provocative thought exercise. If geography is destiny and compute is the future, if the speed of light allows us to untether human intelligence from traditional urban centers, pull up the topographical map tonight. Look past the current financial capitals. Look at the deserts, the high steppes, the volcanic rifts, and the mountain rivers. Given the massive forces we've unpacked today, where do you think the next great metropolis of human intelligence is going to be physically built? Thank you so much for joining us on this deep dive. We'll catch you next time.